Hey, I'm here today to teach a lesson of torque. Alright, so there's a few things with torque. So torque it has to do with physics. So torque is a twist or turn that tends to produce rotation. Basically, you find these applied to common tools every day to turn, tighten, or loosen devices even. So basically the definition of torque is it's a force that causes change in rotation or motion. An example of that could be a tool such as a wrench, maybe even a door, or maybe even just turning on your faucet. There's three things that determine the torque of anything. So basically the magnitude of an applied force, of that force. And then so the direction of applied forces and the location of where that force is applied to. Those are the three factors that'll affect your whole torque and how it's working. So the direction for torque. So torque is a vector quantity, which means that has direction as well as magnitude. There's positive torque and there's negative torque. When you have positive torque, you have counterclockwise, and when you have negative torque, you have clockwise. So and then there's units for torque, obviously, because you can't forget it. It's just like newtons with forces. So torque is proportional to the magnitude of F and to the distance from the axis, which is the radius. Thus, a tentative formula might be T equals F times R, T being torque, F being force, and R being radius. So and then there's only one concept left for torque, which is equilibrium, which means the torque on the left side of something and the torque on the right side of something equals the same amount. I'm here today again to teach another lesson about uniform circular motion. Alright, basically uniform circular motion is motion along the circular path in which there is no change in speed, only in direction. Constant velocity is tangent to the path, and the constant force is towards the center. Circular motion is basically a circular path, basically. So with these two circles, it's basically saying, all right, right here is your force towards the middle, and the outside is the velocity right here, the constant velocity tangent to the path. All right. So the question of an outward force can be resolved by asking what happens when the string breaks. Now this is what happens when the string breaks. So you're spinning the string right in a circular path. You cut the rope at this point, and it keeps going in the same direction, tangent to the path it was going. So when the ball moves tangent to the path, not outward as people might expect it right here, it wouldn't keep going. It just wouldn't happen. So when centripetal force is removed, the ball will continue in a straight line. Centripetal force is needed only to change direction. So the definition of this whole thing, there's a few ways to derive the acceleration from circular motion. So first we have centripetal acceleration right here is equal to the velocity over time. And then with similar triangles, you have the change in velocity over velocity equals seconds over radius. Right here we have just the breakdown of it. And then right here is what we really need to worry about. The centripetal acceleration would equal v squared over r. And for centripetal force, it would be Fc, well, just big F, little c, equals mv squared over r. Alright, so I'm here once again, to teach you a small quick lesson about gravitational force. Alright, so the definition of gravitational force is it's a very long range but relatively weak fundamental force of attraction that acts between all particles that have mass. For example, a big planet, Earth, and Saturn, the gravitational force between them. And that's how you would figure out how strong they are towards each other. So the formula for this is gravitational force equals gravity times mass times the second mass, the second planet or second big mass, over radius squared. All right, now here's an example of what torque would look like. All right, so we have a 20 kilogram girl sitting 3 meters from the center of a teeter-totter. How far must a 50 kilogram boy sit from the center in order to be balanced? So what we're looking for is equilibrium. So what's on one side has to equal the other. So all right, we have the girl, but all right, look, this is what we have to figure out. So force is a weight and weight is a force. So we got to figure out the weight of the girl and the boy. So what we're gonna do is we're gonna plug in the equation W equals mass times gravity. So right here we have a 20 kilogram girl, so we're gonna plug in 20 and 10 for gravity, because that's how gravity is. And so the weight of the girl would be 200 newtons in. So for the boy, it would be different. 50 times 10. So 50 times 10 equals 500 newtons. All right, so now that we got the numbers out the way, we have F times R right here. F times R, we have it right here. 200 is F, R is 3. So this is the girl, this is the boy. So whatever is on the left side must equal on this side. So we have 200 times 3, which is 600. We have 500 times R, which would be 500 R. So 600. We need to isolate that. I mean, we need to isolate R. So what we're gonna do is divide by 500 to the other side. So we're gonna cross this out, and then we're gonna cross these two zeros out. So 6 divided by 5 would then be right here. 1.2. All right, so right here we have an example of uniform circular motion. So we have a 3 kilogram rock, and it swings in a circle of radius 5 meters. So if its constant speed is 8 meters per second, 8 meters per second, So what is the centripetal acceleration? All right, so what we're gonna do is draw a little circle, connected to the rock, and then, that's the rock, flies off, So we have centripetal acceleration equals velocity squared over r. So we plug in the 8 right here. We plug in 8 right there, so it'd be 8 squared is equals 64 over 5, because there's nothing to do with the 5. So basically, in the calculator, you plug it in, and you get the centripetal acceleration is 12.8 meters per second squared. All right, now on to the next equation. We have centripetal force, which is mass times velocity squared over r. So what we'd have to plug in for mass 3 kilograms, the rock right here, and then we'd have to plug in the centripetal acceleration we just got. So now with that, 3 times 12.8 would lead to the answer of the force of the centripetal is 38.4 newtons. All right, right here we have an example, a perfect example of gravitational force. We have to determine the gravitational force between Earth and the Moon. All right, so their masses are 5.98 times 10 to the 24th power kilograms. That's Earth. And the second value would be 7.26 times 10 to the 22nd power kilograms. All right, so we have an average distance, which is irrelevant. We don't need that. All right, so right here we have the equation. This is what we need. We need gravity. This is what gravity is right here. Gravity is just a variable that has a number to fill in like pi. All right, so what you do is you just plug it in, and you have the first mass, and then you have 2, which is the moon, and that's Earth. So you can't forget the radius, which is right here, which it didn't turn out to be irrelevant. All right, that's your radius. All right, so now you plug everything gravitational force, you get the 1.96 times 10 to the 20th power newtons. It's the understand.